Greetings humans, we're going to be talking about exponential functions, y equals ab to the x. So, goodness gracious, this is something that's changing by a constant factor. So you've got 3 comma, maybe 9 comma, maybe 27. Goodness gracious, it's getting bigger faster. And that's the point of these exponential functions, because they're changing by a constant factor, not a constant slope or a constant rate of change, like where you're adding 3 every time. Instead, you're going to be multiplying 3 every time, like so. And how might that look? That might look like 3 to the x. You see, if you put in a 1, maybe the value is 3. If you put in a 2 for x, maybe the value is 9, and you see the trend continuing. So you can actually call this y equals 3 to the x, where the a value is there, it's just in disguise. Right now, the a value is 1. So every exponential function will be of the form y equals ab to the x. Let's see what this looks like. Let's see what this looks like when graphing. So we've got this y equals 2 to the x. Wait, I thought you just said it's ab to the x. It still is. Remember, the a is just 1 in this case. As you were to go to the graph, maybe you make a table of x, y values. Maybe you look and see where x is a certain value as it relates to y. I'll put -2, -1, 0, 1, and 2. If I look at my function, which is saying 2 to the x, and I put in a -2 for x, what does that mean? It means 1 over 2 to the second, which is 1/4. And you should be okay with that because of the exponent properties. 2 to the -2 is the same as 1 over 2 to the second. That's where I got this 1/4. And it follows that these values are here. 2 to the 0 would be 1. 2 to the 1 is 2, of course. And 2 to the second, 4. If you go to the graph, it looks kind of funky. Let's see. If you go to -2 on the graph, you see that the value is only 1/4. -1, the value is half. When we get to 0, it's 1. As you go to 1, it's 2. And notice how it's growing ever so quickly as you move in the positive x's. So it looks like this will be following a trend of getting really small as you grow close to the x-axis on the left, but really big as you go on the x-axis to the right. Question: will this ever be below 0? Is there anything I can put in for x up there that will allow the value for y to be 0 or less than 0? Think about it. If you put in a number here that's right here, if you put in a number for x that's positive, like 1, 2, 3, it's just going to get really big. If you put in a number right here for x that's 0, it's just going to be 1. If you put in a number right here for x that's a negative number, like -1, -2, -3, as you see, a negative exponent just changes the number to a fraction, a positive fraction. So really, this thing will never, as it looks right now, it'll never dip below this x-axis. Interesting. Fun fact about exponential functions of this form, y equals ab to the x. Okie dokie humans, let's take a look at the graph of this function. And again, it's an exponential function. That just means that as you put in a value for x, it's actually the exponent of some constant factor that's being repeated with multiplication because it's exponential. and then maybe you're multiplying by some idea of a. If you put this in the chart, a little t-table here, with some value, independent value for x, will affect y. As you put in values for x, I'll go with the standard -2, -1, 0, 1, and 2. As you put in a -2 for x, notice again that you have something that has a negative exponent. So it's best to change the form as it's 1 over 3 to the second, which is 1 over 9. And you still have to multiply that idea by the 2 that's next to it. 2/9. When you've got 3 to the -1, that's 1 over 3 to the +1 times 2, which is 2/3. And you got to continue in this manner. Be careful here. You've got 3 to the 0, but then you've got to multiply it by 2. So really, when x is 0, y is 2. 3 to the first, multiply it by 2 for 6. And then 3 to the second, 9. Multiply it by 2 is 18. So to graph these things, it's just as easy as graphing anything else. You have an x value. You put it into your function. The function operates on x and achieves a unique y. -2, the value is 2/9, so really close to this x-axis. -1 for 2/3, slightly bigger. And see, my scale for y is as it is. It's going up by 3 because, as you notice, 0, 2, we're going to start to get really big really fast. 1, 6, and then 2 goes all the way up to 18. These exponential functions, if you ever heard anybody say that the growth is exponential, they mean business. They mean it's growing pretty substantially. As you see these things, again, it'll tend toward, as you move left on the x-axis, as your x value gets smaller and smaller and smaller, the value of your function gets ever closer to 0, but it'll actually never touch 0. And we describe that by way of how these functions are behaving. You've got an x value over here that's positive, so as you move to the right on the x-axis, as you're talking about x's that are getting bigger and bigger, of course your function will be getting bigger and bigger because you're taking some number to some power, and if that power is big and positive, that number is going to be big and positive if that number is positive itself. Okay, something I want you to notice about this. The a value here is 2. And guess where the y-intercept was? Interesting. And if you remember from the last equation, the last function, we had y equals, what was it? Was it 2 to the x? And you remember its a value was 1. If you go back and look at it, sure enough, the y-intercept was at 1. And I hope you can see why that makes sense. It makes sense because if you have an x value, plug in here, x value at 0, that's going to be a y value on the y-axis. As x is 0, the value for y will be the y value that lies on the y-axis. So if x is 0 in this case, that means this thing has a value of 2 to the 0 is 1, and 1 times whatever's out in front will be whatever's out in front. So with these exponential functions, as x is 0, you'll find that y must be this value for a. Huh, interesting. Uh-oh, game changer. We've got an exponential function, of course, y equals a times b to the x. It's of that form. And I hope you're thinking right now, you'd know exactly where to plot that y-intercept. The y-intercept, of course, should be the value where x is 0, right? So you could put a 0 right in here and figure out what the y-intercept would be, and by now, hopefully you know that it's always this number here. But in the meantime, let's pretend like we don't know how to do that. Let's go to our t-table. Let's put in our function, -4th times 6, that's a 6, to the x. and put in your standard generic values here at -2, -1, 0, 1, and 2. As you take 1/4, that's negative, and multiply it by 6 to the -2. Goodness gracious, that number is pretty small, because watch, you have 1 over 6 to the second, which is 36. And then you have it multiplying 1 over 4. Oh my. 120 and 44. 144, that is, oh, wait a second, this is negative, because this 1/4 is negative. So it's actually the number that's really close to the y-axis, where x is 2, 1, and 2. Really close to the y-axis, but in negative land. So maybe right in there, super close to the y-axis. Okay, let's see what else we've got going on here. As you put in -4, so you put in -1 over here, you've got 1 over 6 multiplying 1/4, and remember, that's negative. So it's -1/24. So that got substantially bigger, but still very small. Okay, and now when we plug in the 0, we should be able to figure out where the y-intercept is, and we should already know if we have identified what A is. And of course, it's that -1/4, because 6 to the 0 is just 1. So the y-intercept crosses at 1/4. So these are really small values here. Let's make this bigger just to compensate. That should be around there. This should be around 1/4, even though it looks like it's at 1/2. And there we have it. When x becomes 1, you can see that this thing is getting a little bit smaller. Here we go. This looks like just 6 over 4, right? And then lastly, we have 6 to the second power multiplying 1/4, that's negative. 36 multiplying 1/4 is 9, but negative. And remember, this one's negative as well. We've got 6 over 4, which is 3 over 2, which is 1.5. So when the x value is 1, the y value is -1/2. And when the x value is 2, the y value is all the way back down to 9, so somewhere down in here. Now, this makes sense here, but does it keep on going up and up, or does it never ever pass the x-axis? I don't think it crosses the x-axis this way either. And maybe that makes sense if you go back and inspect what would happen when you plug stuff in here for x. The only way it's going to cross that x-axis is if something happens outside of your function, meaning something happens out here when you add or subtract some number. We'll call it d for the time being. Hopefully this makes sense, the graphing of these exponential functions. I have one more thing to show you. The last thing I want to talk about is exponential growth. We've talked about exponential functions of the form y equals ab to the x. Now I want to specifically talk about when your function will be growing. You will have it of the form a, just like before, but we're going to ensure the fact that it's growing by a certain rate as it relates to a certain time. So the rate will be some fixed number, a percentage of growth. Say you have a mutual fund that on average grows about 7% a year. You'd put that number, that percent, in there as a decimal. Be sure to change it to a decimal before you start interacting with this here number in there. And this number here is the principal amount, or the initial amount, whatever you want that to be. If your population of zebras is growing by a certain percent a year, you'd put the starting amount of zebras as you started to observe them, and then the rate of change in this case would be the rate as a percentage. And lastly, you have this idea for t, which is usually annually, in years, the amount of time in years. And I guess it could be however many times you're seeing this rate, this percentage rate happen. So it doesn't necessarily have to be years, but usually you'll see it in years. So, an example of a question like this, like I said, let's go with the zebras. You've got zebras, you've got 20 of them that live in a house in Florida, and they're growing at 8% a year. Okay. How many zebras will you have at the end of, I don't know, 5 years? Good question. Let's go to the formula. Because you can see here, this is saying we're growing at 8%, so we know it's an exponential growth problem. And we've got 5 years at 8%, and we started with 20. So very self-explanatory. 20 goes in for where we started, or the principal amount. 1 plus 8% as a decimal taken to the 5th power. So really you've got 1.08 to the 5th, whatever that is. If you multiply that by 20, you should get your answer. And I think it's 29.4 zebras. So maybe if you were answering this question, it looks like one of them is pregnant, I guess. So it looks like 29 zebras is what you would have at the end of 5 years, and maybe they needed to build an extension on their house, because that's where they were leaving. I've spoken too much on this video. Hopefully it helped shed some light on these exponential functions and how they grow and what they do, specifically related to the graph. You've got a couple of word problems with your homework. Hooray for words. And I'll see you sometime in the future. Goodbye.